Okay, we're going to talk about the characteristics of acids and bases. Well, if we look at a T-chart for acids and bases, we can see that acids taste sour. Think about lemons. Lemons are very sour. And bases taste bitter. Soap is a base, and if you've ever accidentally gotten soap in your mouth, you know that soap is very bitter. Another characteristic is bases feel slippery. And again, we refer back to soap. When you have soap on your hands, you know your hands are very slippery. Okay, so now let's talk about litmus paper. Litmus paper is a type of indicator. It has a special chemical in the paper that turns color. And when we have red litmus paper, it doesn't change colors. It stays red in an acid. But if you use blue litmus paper, it will turn red. So we can associate acid with the color red. And just the opposite is true for bases. If we have red litmus paper, it will turn it blue. In blue litmus paper, there's no change, so we can associate bases with the color blue on litmus paper. Okay, another characteristic is that an acid plus a base, if you mix an acid and a base together, you're always going to get water and a salt. And we don't necessarily mean table salt like sodium chloride. We mean any ionic bond between a cation and an anion. That's called a salt. And the last characteristic we want to talk about is when you have acid and you put an active metal in this acid, it's going to start going through a chemical reaction and it's going to be releasing hydrogen gas. Okay, and there's really three types of acids and bases, and those three types are Lewis, Arrhenius, and Bronsted-Lowry. But we're not going to talk about three types, we're only going to talk about two. So we're going to cross out Lewis because we're not going to talk about Lewis acids and bases. So let's get a definition of an Arrhenius acid. An Arrhenius acid is any compound that dissociates into a proton, which is the hydrogen without an electron, so it's just H plus and an anion. And we have a reaction here. If we were to put hydrochloric acid into some water, it's going to completely dissociate into hydrogen ions and chlorine ions and the water. So simply, if it begins with an H, then it's an acid. And there's only one exception to that, and that's acetic acid. And these are the formulas. There's three different ways to write acetic acid. These are the formulas, and we can see here that none of these three begin with an H. But acetic acid is an acid. You just have to remember that. You just have to memorize it. Okay, now an Arrhenius. Oh, and there's the H. Okay, that fulfills the definition of an Arrhenius acid. Okay, an Arrhenius base is any compound that dissociates into a cation and an OH ion, a hydroxide ion. So if we were to take sodium hydroxide and put it into water, we'll get sodium, and then we're going to get that hydroxide ion right there in water. Okay, so simply if it ends in OH, then it's a base, like NaOH. Now Bronsted-Lowry is a little different. You just can't look at an acid or a base and tell if it's Bronsted-Lowry acid or Bronsted-Lowry base. A Bronsted-Lowry acid is a proton donor. So we're just talking about hydrogen only. Okay, hydrogen only. The acid is the donor, and the Bronsted-Lowry base is a proton acceptor, so it accepts the hydrogen. And Bronsted-Lowry acids and bases are always associated in pairs. You have your acid and a conjugate base, or a base and a conjugate acid. So let's look at a equation. Here we have NH3 plus H2O yields NH4 plus OH. Well, let's look at what we have before and after the reaction. We have NH3 on this side and NH4 on this side. So the NH3 becomes NH4. And how does it do that? Well, because NH3 is a proton acceptor. It accepted a hydrogen. You see, we see the hydrogen change. It was 3 here, and now it's 4, so it accepted a hydrogen. So by definition, proton acceptor is a base. So NH3 is a base, and it becomes NH4, so that's going to be its, right here, base, it's going to be its conjugate acid. Okay? Now, remember, we're only looking at the proton movement. We're not looking at any other element, just the hydrogens. Okay? So let's look at the other side now. We have H2O becomes OH. So how does H2O become OH? Well, it has to lose a proton. Okay, so we have to lose one of the H's here. It has to donate it somewhere to just have one H. So by definition, it's a proton donor. So water here is the acid. Okay, and OH is going to be its conjugate base. Okay, so where is this proton being donated to? That acid's donating? Well, it donates it to the base, NH3. And when it donates it to NH3, then we see NH3 becomes NH4. Okay, so it's always going from acid to base. Okay, so this donates to here, this becomes NH4. Well, now this can donate to this one. The NH4 can donate to the OH, and then the OH becomes H2O. So it's a cycle. It donates to here, becomes NH4, donates to here, goes back, donates, becomes NH4, donates to here, and so it goes over and over. It's a cycle. That's why you have this arrow that's double-ended to tell you that this reaction goes both ways. It's a cycle.